So, Samuel, we've prepped our data. Now what?
Right, Alfred. Now we can actually use our dataset for training. Think of it like feeding our model examples of lung cancer on CT scans.
Feeding it examples? How does that work?
Well, we've transformed the scans into a format our model can understand. It's like translating a language. The model learns patterns and relationships from these examples, eventually distinguishing between healthy and cancerous tissues.
So, what exactly is the model learning? Is it like identifying specific shapes or textures?
Exactly. The model might identify patterns in the pixel intensity, or even subtle variations in tissue density that signal cancer. It's more sophisticated than just shapes or textures, learning complex relationships from enormous amounts of data.
That sounds like a lot of information. How do we know our model is actually learning?
We use metrics, like accuracy and precision. We'll see how well it predicts on unseen data, new CT scans it hasn't encountered before. It's critical to test on fresh data to ensure real-world application.
And what if the model makes a mistake?
Mistakes are inevitable. We'll need to adjust our model or our data to improve accuracy. This iterative process is crucial in machine learning.
Is there a way to explain why the model made a mistake?
Absolutely. That's called model interpretability. We want to be able to understand the reasoning behind the model's predictions, especially in healthcare settings. It's important to avoid a black box effect.
Makes sense. So, using our dataset to train the model is like providing a ton of examples to guide its learning.
Yes, exactly. It's like having a very skilled detective learning to spot cancer clues in medical images.
So, Samuel, this chapter's all about building a model for classifying lung nodules. Sounds pretty straightforward.
Well, it's more nuanced than that. We're laying a strong foundation, Alfred. Think of it like building a skyscraper. We need a sturdy base to add all the features later.
Right. So, this training loop, what's the big idea?
It's a systematic way to teach the model. We use data to adjust its internal weights, improving its accuracy over time. Kind of like practicing a skill, you adjust based on feedback.
And this validation set, why is that crucial?
Validation lets us see how well the model generalizes. It's like testing a student on a different exam than the one they practiced on.
So, you're building a training application and separating dataset code into modules?
Exactly. Complex projects need structure. Keeping code organized is essential. Too little structure and it gets messy. Too much, and you're bogged down in administrative tasks.
Aha! So, a balance.
Exactly. The right amount of structure for your project size. We're focusing on metrics, too.
Metrics?
We're not just seeing how well it performs, but how it's performing. Tracking the loss and classification accuracy is crucial to evaluating our progress. You know, it's like tracking your steps in a fitness app. It helps you understand your progress.
You're saying we're not just looking at the final score?
Absolutely not. We need to watch the metrics evolve throughout the training process. It reveals insights we might not see otherwise, like subtle patterns.
That's an important point. So, how do these metrics help us with experimentation?
With detailed metrics, we can pinpoint which changes improve performance. It helps us diagnose problems or figure out if our ideas really are worthwhile.
So, what if we have limited, messy data? What's the problem there?
Limited and messy data is a big challenge in real-world applications.
I get that, but how does that impact the training process?
It affects how well the model learns. We'll discuss this further in future chapters.
Okay, that makes sense. We'll focus on building this foundation, understanding the training loop, and laying the groundwork for handling limited data. Good stuff, Samuel. So, Samuel, this new application structure, it's modular, right?
Yeah, absolutely. It's designed to be reusable. We're wrapping our training code in a command line application.
Why is that a good idea? It seems a bit extra.
Well, think of it like a toolbox. This way, the training tools are organized. You can easily run them from different places: Jupyter notebooks, command lines, even other Python scripts.
And how does this command line interface work?
The application uses the standard argparse library. That lets you provide options like the number of training epochs or worker processes, right in the command. It's very user-friendly.
So, passing arguments, it sounds like there's an argument parser. Why have the application class handle argument parsing instead of doing it in the main function?
Precisely. It allows flexible configuration. You can set up your application, customize it using arguments, and then use it many different ways.
Like, how would the run function in Jupyter use that?
You pass it the application name, module name, plus any extra arguments to the application.
That's pretty neat. So, you've got a dedicated run function to do this. What does that even look like?
See, it's really about convenience. You use it to run your application and make sure things run smoothly. It neatly packages it up for invocation.
What are the benefits of using a class for this?
Using a class encapsulates the application logic. You can instantiate the class and then use its main method. Testing, debugging, and using it within other programs becomes much easier. You're not spinning up a whole new process for each execution.
So, that's the general structure. How does the main method work?
That's the heart of your application, the place where the core training logic resides. You'd implement the actual training algorithm there.
What about the if underscore underscore name underscore underscore equals equals underscore the main underscore underscore colon block? I see that in the example. What's its purpose?
It's a standard Python idiom. It ensures that the Luna training app.main call only happens when the script is executed directly, not when it's imported as a module into another script.
Okay, Samuel, so we're talking about setting up a training process. You mentioned initializing the model and optimizer. Can you unpack that a bit?
Sure. First, you gotta create the model itself. Think of it like building a house. You need the blueprint, the model architecture.
Right. And then what about the optimizer?
The optimizer is like the construction crew. It figures out how to adjust the model's parameters to fit the data better, like fine-tuning the house to best suit the site.
So, initializing the dataset and data loader, what's up with that?
That's about getting the materials ready. The dataset is like the lumber yard, holding all the building blocks, the training data. The data loader is the delivery system, getting the lumber to the construction site, your application, in manageable batches.
So why batches? Why not just dump the whole dataset?
Efficiency, man. Processing all the data at once can be super slow. Batches make things way quicker. And the training data is usually pretty big.
Makes sense. What about randomizing the samples?
Randomizing shuffles up the training data. It helps prevent the model from memorizing the order of the data. You want the model to learn general patterns, not specific examples.
Clever. So, we've got the model, the optimizer, the dataset, and the data loader. Why is that important?
That's the core foundation. Without these, you can't start the training loop. It's like trying to build a house without the blueprint, the crew, the materials, or a way to transport the materials.
Got it. This is crucial. So, we're not just throwing random code together?
No. It's structured like a recipe. Every step counts. You need the right ingredients, the right tools, the right process. Good organization is key here.
Excellent point. Thanks, Samuel. So, Samuel, we're diving into initializing our deep learning model. What's the first crucial step?
Setting up the hardware, Alfred. We've got to decide if we're using GPUs, and if so, how many.
Right? Why is that a big deal?
GPUs excel at parallel computations, so it's a massive speedup for complex models. Using them efficiently is key to training large models in reasonable time.
So this data parallel thing, what's its role?
It's a simple way to spread the work across multiple GPUs. Imagine chopping up a big task into smaller pieces, then having each GPU handle one piece.
But isn't that also done with distributed data parallel?
Yeah, but data parallel's simpler, easier to set up, and good enough for single machine scenarios. Distributed data parallel is for when you need multiple machines.
Okay, so if we've got multiple GPUs,
our code automatically distributes the model's calculations to all the available GPUs. It's a neat trick, almost transparent to the user.
So, moving the model to the GPU is important, correct?
Absolutely. You need to tell the model to operate on the GPU memory. Otherwise, calculations would be done on the CPU, which is significantly slower.
Why does the order matter? Putting the model on the GPU before the optimizer?
Yep, The optimizer needs to work with the model parameters on the GPU. Otherwise, it'd try to update parameters on the CPU, and that's a big problem.
And for the optimizer,
We're choosing a straightforward one, stochastic gradient descent, or SGD. It's a tried and true method. It's not the fanciest, but often a good starting point.
why SGD? Aren't there others?
There are, but SGD is a solid baseline. Learning rate and momentum are critical parameters in SGD. Their values are often experimented with to get optimal performance.
Are these hyperparameters we need to change right away?
Not necessarily. These learning rate and momentum values are pretty standard. Starting here works in lots of situations. But for more specific or difficult problems, tuning hyperparameters is the next step.
Makes sense. So, we're starting with a straightforward optimizer and making sure to load our model onto the GPU first. Anything else crucial to remember?
The choice of optimizer, learning rate, and momentum values are not always the best, but they're typically pretty good defaults. A deep dive into hyperparameter tuning is best tackled after we solve other key model issues. That's our next step.
Okay, Samuel, we're talking data loaders now. So, this Luna dataset, this is crucial, right? It's like the translator between our raw CT scan data and PyTorch, which needs things in a specific shape.
Exactly. Our CT scans aren't in the right format for PyTorch to process. The models expect specific dimensions, like number of samples, channels, depth, height, and width. Think of it like a recipe needing specific ingredients.
Gotcha. So, Luna dataset is fixing that, right? Like, adding the missing dimensions.
Precisely. Luna dataset does the initial transformation. Remember that unsqueeze 0. It creates the channel dimension, which CT scans, being single intensity, only need 1.
Right, that's crucial. But why are we batching data too?
Batching is about efficiency. Most computers are better at processing multiple things at once than a single CT scan at a time. Imagine assembling a puzzle. It's faster to assemble multiple puzzle pieces concurrently.
I see. So, instead of processing one CT scan at a time, we process several at once.
Exactly, multiple samples or CT scans, grouped into a batch, which then becomes the input for the model.
So, PyTorch's data loader handles the batching magic? That's brilliant.
Yeah, we don't have to code it ourselves. The data loader takes care of grouping our samples into batches.
So, how do we set the batch size? Is there a magic number?
Not really. We define the batch size based on how much data the GPU can handle, and it's often influenced by the number of GPUs you're using. More GPUs usually means a larger batch size.
Interesting. And how about the number underscore workers? What does that do?
That's key to speeding things up. With number underscore workers, we use separate processes to load data while our model is calculating. We're effectively multitasking data loading with model processing. It makes things incredibly faster, especially with large datasets.
So, we can load batches in parallel. Makes sense. What about the pin underscore memory?
Pin underscore memory makes data transfer to our GPU incredibly fast. It's like ensuring the data is already on the GPU's waiting list, so the transfer is immediate, which speeds up processing time.
Excellent. So, using data loaders gives us the speed boost for large datasets, allowing model training to happen much faster. It's a critical tool for efficiently feeding the hungry GPUs.
Exactly. It's a powerful optimization that is common in deep learning projects, and very important for efficient and quick training.
So, Samuel, you're saying we're using a pre-existing 2D image recognition model? That's smart. How will we adapt it for 3D medical images?
Yeah, Alfred, it's a good starting point. A lot of the core architecture ideas translate really well. We're leveraging existing models, but we'll need to adjust the model. Think of it like slightly modifying a recipe, you know? The base ingredients are useful, but you have to tweak things for a different outcome.
So, what are the key tweaks for 3D?
Well, the input data is now 3D, not 2D. This means we need to adjust the convolutional layers. That's a key point. We have to account for the extra spatial dimension.
Ah, I see. So, not just a simple change, but a fundamental architectural change.
Exactly. We're building on a model from Chapter 8, and this project will be helpful in future projects too. Just like a toolkit. The more complex, though, the more you'll need to customize it.
Okay, so you're saying the overall structure, the backbone, will be similar, but the details like the convolutional layers will change.
Precisely. The figure shows the backbone is made of 4 repeating blocks. Those will adapt.
Makes sense. And this initial model, despite not being perfect, will form the base for future work?
Absolutely. The more complex a project, the more we'll need to adjust. We're building a flexible framework here. Imagine building a house. This first design is the foundation.
Right. And the tail and head of the network? What about those?
The tail is basically post-processing. Batch normalization. The head, well, it's the output layer, a linear layer followed by softmax. Think of it as taking the information and making the final, actionable, classification. Very important.
So, it's like a funnel, gathering and refining information to give a useful output. That's fascinating.
Yep, and this whole approach is highly adaptable. We'll be modifying this framework as we move along and encounter new issues. It's often an iterative process.
Sounds good. So, we're building a modular, adaptable model and using existing knowledge, right?
Exactly. Leveraging past experience and adapting it for this specific task. Think of it as reusing good parts from a machine, upgrading them to fit.
Great, Samuel. This clears it up. So, Samuel, you're talking about these tails, backbones, and heads in classification models. Can you unpack that a bit?
Sure. Imagine a complex image classification task. The tail, those initial layers, are like the pre-processing steps. They prepare the data for the backbone.
Like getting raw images ready for a specific analysis pipeline?
Exactly. They might resize, adjust, or filter the input. It's tailored to what the rest of the network expects. The backbone is the core, containing many layers for feature extraction.
Feature extraction? Like finding those key details to classify images?
Exactly. Each block in the backbone does some level of this work. You've got a repeating pattern.
So, you have this repeating block structure?
Yep, makes things more efficient and reusable.
And the head? What does it do?
It takes the extracted features and converts them into the final output, like the class label.
So, the tail gets the data ready, the backbone extracts features, and the head classifies? That makes sense.
It's a standard architecture. The initial convolutional layers might reduce the input size.
Why would you want to reduce it?
To reduce the complexity of the problem for the rest of the layers.
And they're using 3 by 3 by 3 convolutions? Pretty standard, right?
Very common, especially when you stack them. 2 stacked 3 by 3 by 3 convolutions increase the receptive field.
That's important, right? A larger receptive field can pick up broader features from the input.
Yeah, it lets the model see more of the context around a single pixel/voxel.
You're saying the stacked convolutions effectively behave like a single larger convolution?
Exactly. It's a powerful shortcut for detecting broader features, all in fewer layers.
Interesting. And what about that max pooling at the end?
It downsamples the output further, ignoring some data points, but keeping the most significant.
So, it's like a filter?
Kind of, but not just selecting data. It's finding the maximum value within a region.
That makes sense. And why a ReLU activation function?
It's a way to introduce nonlinearity. ReLU activation helps the network learn more complex functions. Precisely. This block architecture is reusable. You can repeat it several times to build a powerful model.
Sounds efficient. What about the output size? Does padding keep it the same?
Padding is critical. It maintains the size of the input, even though the effective receptive field grows.
That's important. Otherwise, you'd lose crucial information, right?
Exactly. It prevents losing information and keeps things manageable.
Okay, Samuel, let's talk about this model. So, the tail looks pretty straightforward. Normalization. Why is that important here?
Yeah, the tail's pretty standard. You know that input data might be in some weird units, like Hounsfield units for medical images. Normalization makes sure that all those different scales don't mess with the learning process. It makes everything fair and consistent.
So, it levels the playing field, essentially?
Exactly. It shifts and scales the data so the mean is 0 and standard deviations 1. Makes the network's job easier.
Interesting. And the backbone. Those 4 blocks. Why 4? Is there a rule of thumb for this?
Not exactly a hard and fast rule. It depends on the resolution of the image and the complexity of the task. You know, each block downsamples the image. After 4 blocks, your 32 by 48 by 48 input is drastically reduced. It's a bit like zooming in to a small portion of the image while still capturing all the important information.
So a 16x reduction. That's a big step. Makes sense for some image recognition.
Absolutely. The goal of the backbone is to extract the essential features, not get every single pixel. That reduction in resolution helps with memory and computational efficiency.
Okay, so these 2 by 3 by 3 pixels by the end, what do you do with that?
You're right, that's where things get interesting. These aren't just any old pixels. They're representations of important features from the image.
Ah, the flattening process? Why do we need to flatten this 2 by 3 by 3 image with 64 channels?
Fully connected layers only understand one-dimensional vectors. So we need to rearrange the 2x3x3x64 data into a single vector. That's what the dot view function does. It's like taking a multi-dimensional array and turning it into a flat list.
Right, so it's the bridge between the convolutional part and the final classification layer. Makes sense.
Yep, it's the essential step to get the data into a format that the fully connected layer can handle.
And the softmax? Super important. Can you unpack that function?
Absolutely. Softmax squashes all the network's outputs, logits, into probabilities between 0 and 1. Think of it as a way to express certainty.
So, it converts the raw outputs into a more digestible form?
Exactly. And importantly, it only cares about relative differences in the logits, not the overall scale.
Why do we need both logits and probabilities?
Logits are for training, using the cross-entropy loss function. And the probabilities are for classification in the final result. They're the probabilities, the answers.
Initialization. What's the deal there?
Well, in networks, if all the weights are too big, outputs blow up, learning gets messed up, like a runaway train. Or if they're too small, the values get lost and nothing works. We need to initialize weights in a way that keeps intermediate values and gradients in a good range. PyTorch doesn't do it automatically.
So, you have to do it yourself? That seems complicated.
Yeah, but we use k-normal_normal_ function, a standard technique. It gives the network a better start. It's a sort of good enough initialization. It's not magic, but it helps prevent those runaway values.
Okay, Samuel, so we're diving into the training loop now. This looks pretty sophisticated. Can you break down the main components?
Sure, Alfred. The core idea is familiar, epochs and batches. We're essentially iterating through our data to adjust model weights.
Right, but this loop's got some extra bells and whistles. What's this tier in metrics_G tensor?
It keeps track of metrics for each class during training.
Interesting. So, it collects data, like accuracy for each category?
Precisely. This detailed information is great for larger models. It provides insight beyond just the general loss value.
And this enumerate with estimate function? It sounds like it adds a time estimate?
Yeah, it's a slightly enhanced version of enumerate. It gives you an estimate of how long the training process will take. Helps you plan, you know?
Makes sense. So, the actual loss calculation is in a separate method. Why the separation?
Codereuse. Compute batch loss handles calculating loss for each batch. This keeps the do training function cleaner, more manageable. It's easier to debug and change in the future.
You're saying it's good practice to avoid code duplication? Got it.
Exactly. Reduces errors and improves code maintainability. This way, you can easily modify loss calculations without touching many other parts of your code.
Okay, that makes sense. But we're skipping directly over the data loader. Why not iterate over the data loader directly?
Good point, Alfred. Enumerate with estimate is a stylistic choice. It's not necessary for the algorithm, but it does provide a better user experience. Gives you that time estimate for planning.
So, this is like a performance optimization, but not crucial to the algorithm?
Precisely. It's a way to add a user-friendly touch to the training process, which is great for tracking things out. And that's important for tracking your progress.
I see. It's a trade-off between cleaner code and extra functionality. So, we're keeping things manageable and user-friendly. What about potential pitfalls in this approach?
Well, the enumerate with estimate function could become a bottleneck if it's poorly implemented. But if it's optimized well, it will add value. Essentially, make sure you're doing it right.
Okay, Samuel, so this compute batch loss function, it's crucial for training, right? Tell us more about how it works.
Yeah, it's a core piece. It takes a batch of data and calculates the loss for that entire batch.
So, it's not just a single sample?
Exactly. It processes a group of samples. And crucially, it computes the loss for each sample in the batch. This is key.
Why is calculating the loss for each sample important?
Because you can see how the model is performing on individual data points. Imagine trying to identify different types of cats. This way you'll see if the model misclassifies a specific tabby or Siamese, not just the overall accuracy. You can analyze the errors and figure out where your model is getting confused.
So, you're breaking down the batch's loss into individual losses?
Exactly. This allows us to keep track of each sample's prediction performance, including where the mistakes are happening and why. Then, you can use that information to improve the model.
You're using cross-entropy loss? What's the significance of that?
Yeah, we're using it to measure the difference between the model's predictions and the actual labels. It's a common choice for classification tasks. Reduction equals none is the key part though. It gives the loss for every single data point, instead of the average.
So, you get a loss value for each example in the batch. Then what?
We return the mean of these individual losses to get the average batch loss. You can use either the individual or the average loss depending on what you need.
You're also storing the predicted class probabilities and the actual labels, right?
That's right. We record those for each sample. This is how we can compute accuracy or metrics for each class, to see where it's getting it right and where it's having problems. It's like having a detailed scorecard for each sample.
And why are you detaching those values?
Because we don't want to keep track of the gradients for those values. We only care about them in the context of calculating the loss, not for backpropagation and updating the model weights.
And those labels, predictions, and losses are stored for later analysis.
Precisely. This lets us analyze the model's performance in much more detail, like identifying the samples that the model misclassified and then investigate why.
So, a wealth of information. That's powerful. And there's practical implications beyond just seeing the model's general accuracy?
Absolutely. You can drill down into specific classes and even specific samples. It's not just about the average performance. It's about understanding where the errors come from.
So, Samuel, the validation loop is similar to the training loop, right? But it's simpler?
Yeah, exactly. It does almost the same steps, but it's read-only.
Read-only? What does that mean?
You don't update the model's weights during validation. It's like you're checking the model's performance without actually changing it.
So, no backpropagation?
Exactly. Crucially, no backpropagation or weight updates. It's all about evaluating how well the model performs on data it hasn't seen before.
And why is that important?
Well, if you updated the weights during validation, you'd be cheating. You'd be overfitting to the validation set, and you wouldn't have a true measure of how well the model performs on new data.
That makes perfect sense. So, the crucial difference in the code you were showing, it's basically a no_grad context?
That's right, Alfred. The with torch, no_grad, statement prevents PyTorch from calculating gradients and doing backprop on validation data. It speeds things up too. The validation set is there for assessing the model without changing it, which helps avoid overfitting. You're essentially freezing the model's parameters and just letting it predict.
You mentioned metrics being collected. What are these metrics?
They're measurements of how well the model is doing, like the loss or accuracy on various types of inputs. We gather statistics on these during the validation run.
Right, so we evaluate the model without adjusting it. Then, We just collect the validation metrics for analysis and reporting?
Yep, exactly. That's the key point. We're not tweaking the model, we're observing it. That validation data tells us if our model will work well on unseen data.
So, compute batch loss is still called in the validation loop, but nothing happens to the weights based on its results?
Precisely. We call compute batch loss, but we don't use the returned loss value to update the weights. We just use it to collect the validation metrics. It's a bit like taking the model's pulse without giving it medicine.
I see. That clarifies the validation loop. It's all about gathering information without altering the model. So, Samuel, we're logging performance metrics. Why is that crucial?
Crucial. Alphat. If training's not working, we need to know ASAP. Logging metrics lets us spot problems quickly.
Like, what kinds of problems?
Like, if the model's not improving, or if it's diverging wildly. We don't want to waste time on a bad model.
Right, makes sense. So, we're collecting these metrics per epoch?
Precisely. Each epoch, we gather training and validation results.
And what's an epoch, anyway?
An epoch is one complete pass through all the training data. It's kind of like a full cycle of learning.
Gotcha. And how do these metrics help us understand the model's performance?
We're looking at things like the accuracy and the average loss across different classes. So it's not just a simple overall number, it's granular by each class.
So, are we using these metrics to decide when to stop training?
Well, not always. But, if things are going badly, yes. And even in cases of stable improvements, they help us understand how the model is performing.
This sounds pretty standard, but are there any potential pitfalls in this process?
Sure. Using epochs this way, you're making a simplifying assumption. We might collect results too frequently. The time it takes to calculate the metrics can affect the entire training process.
So, how often should we log these metrics?
That depends. We need a balance. Too often, and things slow down. Too little, and we miss problems early. It's an experiment, and more information later can refine this.
So it's about finding that sweet spot?
Exactly. It's a dynamic process, and as you know, there isn't a perfect answer in all cases. But the approach is critical to avoid wasted training time.
I see. This approach is about efficient, informed training, not just blindly running code, right?
Exactly, Alfred. We're learning from the process itself.
Okay, Samuel, let's dive into this log metrics function. It sounds crucial for tracking results. What's the core purpose?
Right. It's a function for logging training and validation metrics. Think of it like a dashboard for our model. It keeps tabs on things like loss and accuracy.
Got it. So, it collects performance data?
Precisely. And it breaks the data down by different categories, overall for negative, non-nodule cases, and positive nodule cases, to provide a detailed picture of performance. This is important for understanding which parts of our model are struggling.
Interesting. You mentioned different types of samples. Can you explain these nodule and non-nodule labels?
Sure. In this medical imaging application, we're trying to identify nodules in scans. Nodules are problematic areas. Non-nodule samples are just normal tissue. So we're essentially looking for binary classifications, which makes sense.
Okay, so we have data related to labels. What are the labels represented as in the input?
The input, metrics_t, contains data for labels, predictions, and losses. Think of it like a spreadsheet with columns for each. The labels are either 0.0, non-nodule, or 1.0, nodule. Our predictions are probabilities between 0 and 1.
Makes sense. And how does it use this data to get metrics?
It creates masks. Imagine selecting specific rows in a spreadsheet based on criteria. The masks filter the data based on label or predicted class. For example, we create a mask to focus only on samples predicted as negative cases.
And what happens next?
Using these masks, we calculate statistics like the number of correct classifications per class and the average loss for each class. It's all about evaluating model performance, specifically how well it separates positive and negative cases.
So, it's not just the overall loss. It's about evaluating per class performance?
Exactly. Understanding how the model handles different classes can pinpoint if the model struggles with one over another. The logging shows both overall performance metrics and those broken down by negative and positive labels.
That's helpful. So, it's all about helping us tune the model based on these precise measurements?
Exactly. By looking at the different losses and correct classification rates, we can see how to improve its accuracy and specifically address any weaknesses.
You said it calculates the accuracy? How is that calculated?
It counts the number of correct predictions for negative and positive cases, then divides by the total count, all multiplied by 100 for percentage.
Excellent. Thanks, Samuel. That really clarifies the log metrics function. Okay, Samuel, so we're now ready to run the training script. Tell us, what's the overall goal here?
We're initializing and training our model. Crucially, this run gives us insights into training progress.
So, we're not just blindly running things? It's about monitoring?
Exactly. We want to see how well the model is learning. It's a crucial step in evaluating our model's performance.
And this is done from the main directory? What are the dependencies?
Yes, from the main code directory, with specific subdirectories. The Python environment must have all the libraries listed in requirements.txt. It's standard procedure for a project.
Okay, so, how do we actually execute the script?
We use a command like Python, mp2ch11.trainingq. Windows users have different syntax.
That's useful to know. And what's the purpose of the epochs flag?
That parameter limits the number of training epochs.
So we can control how long the model trains. What else do we see in the output?
We see things like batch size, number of channels, training samples, and validation samples. It's all about tracking progress.
Interesting. So we're seeing how the model performs over time. What if the first epoch is extremely slow?
That might indicate problems preparing cache data for the model. Check if the data's ready. Sometimes, a pre-processing step, pre-stuffing the cache, is necessary for efficient training.
Okay, so pre-processing is important for efficient training. And if the CPU usage is high?
If the 8 worker processes are hogging CPU, the cache might be the issue. We want the GPU to be the bottleneck.
How do we find out where the bottleneck lies?
After the script starts training, look at top and NVIDIA SME. Monitor GPU utilization. Look for output like E1 training.
So we want the GPU to be saturated, right?
Ideally, yes. We want the GPU busy, not the CPU. A GTX 1080 should complete an epoch under 15 minutes for this model. But for larger models, CPU processing might be the bottleneck first.
That makes perfect sense. So, in essence, running the script gives us vital data, tells us where our potential issues lie, and helps to optimize training.
Precisely. Crucial for getting a working performant model.
Okay, Samuel, we're looking at dataset issues. Seems like sample sizes are a concern.
Yeah, checking for enough training and validation samples is crucial.
Why 495,958 and 55,107? What's the significance of these numbers?
Well, those are likely minimum thresholds for effective training. Insufficient samples could lead to poor model performance, possibly even failure.
So, what kind of sanity checks might we perform?
You know, we should verify the data's completeness. Maybe count files manually, or use scripts to do the counting automatically.
So, that initial directory structure, data unversioned /part2/Luna, looks complicated. Subset 0, subset 1, subset 9. What are these subsets?
It's a common way to organize large datasets. Subsets for training, validation, or different parts of the data. You might also have a separate test set.
And the ls commands are looking at these subsets?
Right, we're checking the number of files in each subset. A mismatch could signal missing data.
The output shows 1776 total files across subsets. That checks out. But the subsets have 178, 176, and another number.
Those numbers should add up correctly. It's good to see consistency. It's important to verify that those counts reflect the total expected data.
So if these counts don't add up, we've got a problem.
Absolutely. Missing data or a corrupted structure could be the issue.
And that last line about manning livebook. What does that mean?
If you've checked your data and still have problems, Manning Livebook is an online forum, likely for users of their books or courses. You might find others who've encountered similar issues.
Makes sense. So, crucial steps for verifying our dataset then: check the total sample counts, examine each subset and their counts. Double-check there are expected files.
Exactly. This preventative approach can save a lot of headache later on, believe me.
So, Samuel, this enumerate with estimate function, it's crucial for deep learning projects, right? Why is it so important?
Yeah, Alfred, it's about managing expectations during long training runs. Deep learning models can take hours, even days to train. You want to know if you're on track.
Right, so you need some sort of progress tracker. But this isn't just a counter, is it?
No, it estimates how much longer the process will take.
So, it predicts the future almost. How does it do that?
It looks at the timing of previous iterations and uses statistical methods to predict the time left. You feed in a list of things to process, like images or data points, and it shows how long each part takes.
So, it looks at the patterns of past behavior?
Exactly. The function learns the time spent on each task, and that allows for estimation of the total time.
That's interesting. And if something is taking longer than predicted?
Well, that's a big warning sign. Maybe there's a problem in the model, or maybe the data's more complex than you thought.
So, the warning is not just about the time, but also about unexpected issues?
Exactly. It alerts you if the time estimate is significantly different from what you expected, giving you time to troubleshoot and adjust.
So, the function isn't just providing time, it's also a diagnostic tool?
Absolutely. The time estimate itself is a clue to potential problems with the training process.
Makes sense. And what about the example? The one with 234 iterations taking about 2 minutes.
That's pretty normal, for a project using enumerate with estimate. The function, well, works on these long operations.
So it doesn't just passively count, it actually has built-in estimations?
Precisely. It's a dynamic estimator that gets increasingly accurate as the process continues. With more repetitive tasks, the estimates are highly accurate.
So, the whole idea is a better user experience for someone trying to train an algorithm, giving a sense of where things are headed.
Exactly. You get a sense of control and anticipation, which is important for avoiding frustration. Also, you can check on things while the computer is working. This is essential for preventing wasted time if a deep learning model is underperforming.
A good point. So you're not just showing the progress of the work, you're helping people keep track of their progress, which also improves the efficiency of the project.
Absolutely. It gives you a heads up on things that might be taking longer than they should and allows you to potentially correct them before they cause significant problems, or at least prevent you from wasting time on a failed experiment.
So, 99.7% accuracy. That seems great, but the results are concerning.
Yeah, that high percentage can be misleading. It's like saying 99.7% of people don't have cancer. That's true, but it doesn't tell you much about the rare cases.
Right, but the report shows the model misclassifies nodules. It keeps saying not a nodule. Why is that?
It's a fundamental issue in training. The model is learning to ignore the rare cases. It focuses on the easy part, which is identifying the negatives, so it keeps saying not a nodule.
So, what's really happening? How does this even happen?
The model learns patterns in the data. If most of your data says not a nodule, the model prioritizes that. It sees lots of not a nodule and learns to predict not a nodule for new unseen cases, even if they might be a nodule.
So, it's optimizing for the common case?
Precisely. In medical diagnoses, this is catastrophic. We need the model to detect rare cases, too. The validation set highlights this. It's a major flaw in our model.
And the losses are so high on positive samples. How is that possible?
It's exactly as we see. The loss on the negative samples is almost zero, while the positive samples are disastrous. So the model is almost perfect at classifying what isn't a nodule, but hopeless at recognizing what is.
Is there any way to fix it? What's the solution here?
We need to adjust the training data or methods. Potentially, adding more positive examples, or changing how the model learns. We could also use specialized techniques to balance the training data and ensure those rare cases are weighted correctly for the model.
This highlights a crucial point about evaluation. We need to look beyond simple accuracy metrics.
Absolutely. The validation data loss is a strong indicator of the issue. The numbers are misleading, in this case. Focusing on detailed breakdowns of various sample types is crucial.
So, we need to refine our evaluation metrics as well as our training process.
Exactly. We need to ensure the model focuses on both common and uncommon cases. A balanced dataset and the right kind of learning algorithm are very important.
So, TensorBoard, right? A tool to visualize training metrics. How does this help us, Samuel?
Yeah, it's super useful. Imagine trying to understand your model's progress just by looking at numbers from each epoch. It's like trying to read a weather report just from the temperature. You need a graph to see trends.
Right, like a graph of how loss changes over time. What's the value here?
You quickly spot patterns in training and validation loss. Are they decreasing? Are there weird spikes? Is it converging well?
So, it visualizes training data in a dashboard?
Exactly. It gives a holistic view of how your model is learning, not just a snapshot. It makes it way easier to find outliers and see patterns in learning curves.
Why not just use the training printouts?
Printouts are good for a quick glance, but TensorBoard lets you look at multiple runs, compare them visually, and spot problems or improvements much faster.
How does it work? Does it hook into our code directly?
It's not directly embedded in PyTorch, but TensorBoard devs added official support. You feed your training metrics, think loss, accuracy, etc., into it. It handles the display.
So, we record those metrics somewhere?
Yep, your training scripts usually write the metrics to a directory called runs. TensorBoard finds these files.
How do we install it?
Install the TensorFlow package. You don't actually need TensorFlow for PyTorch work, so you can install the standard CPU version if you're not working with GPU.
What does running it look like?
You run the command TensorBoard log_run/. It tells TensorBoard where your training data is.
And then we see a graph?
Precisely. You'll get a web page, TensorBoard's main dashboard. It shows lots of graphs, including scalars, which display metrics over time.
How do we choose what's displayed?
You select the different runs you want to see on the dashboard. You can even smooth out noisy data.
And what are some of the possible problems we might see on the graph?
Look for flat lines, meaning your model isn't learning. Rapid increases and decreases in loss could indicate issues. You can even compare your training and validation runs, and look for patterns like the validation loss getting worse after some point in training.
How important is keeping our data organized?
Very. If you have too many runs, things get messy. That's why you should keep runs organized, remove those you don't need, and rename or move interesting ones to a different directory, so they don't get deleted accidentally.
So, TensorBoard connects the dots to training metrics. It turns raw numbers into something we can understand quickly. What's the big takeaway?
It's all about efficiently understanding what's happening in your models, whether they are learning, or what is wrong with the learning process. It's a key tool for getting a visual grasp of your training process and makes it much easier to understand patterns, outliers, and issues with convergence.
So, Samuel, you're adding TensorBoard support. Why is that important?
Well, Alfred, visualizing training progress is crucial. TensorBoard lets us see how our model's metrics are changing over time. It's like having a dashboard for our training process.
Okay, but how exactly does this TensorBoard stuff work?
We use this module, torch.utils.tensorboard. It handles storing data in a format TensorBoard can read.
So, we're not just looking at numbers, we're getting graphs?
Exactly. We create these summary writer objects. Think of them as the channels for our metrics data.
And how do we initialize them? That's key.
We pass in the log directory. Crucially, we create separate writers for training and validation data, which helps us compare results. Also, we wait to initialize them until the first run to avoid messy logs.
I see the code creates folders for those. So, why wait to create them until the first run?
If training crashes early, TensorBoard would show empty runs. By waiting, we avoid cluttering the visualization interface with useless information.
Right, this makes sense. The first epoch is tricky. Why skip it when logging metrics?
Well, the initial training data is often random. That's why we avoid logging it. TensorBoard smoothing helps, but skipping it is another way to get a clearer trend. It's a good trade-off.
Right, you want to present clear trends, not early noise. Why use training samples as global steps instead of epochs?
The number of training samples is a better global step. You know, changing the number of samples per epoch doesn't change the model's effectiveness, but it changes how many samples the model sees before a particular epoch's data. Using samples as the global step is more directly linked to the data seen by the model. It gives a consistent measure.
Got it. So, we're basically plotting our metrics, loss, accuracy, and so on against the number of samples processed. That makes sense. So, this is better than just epoch numbers, which can be misleading.
Absolutely. Epoch numbers don't reflect the model's actual training progress if epochs vary in length.
Great. Thanks, Samuel. That makes TensorBoard visualization much clearer. So, Samuel, you're saying our model's not actually learning to spot nodules?
Yeah, Alfred. It's a bit like a student memorizing old exam questions. They might get a high score, but they haven't truly grasped the material.
So, it's not really learning the concept of a nodule?
Exactly. The model's seeing a huge majority of cases are negative. It's learning to output false more than anything else, which is incredibly efficient, but ultimately misleading.
But the loss is decreasing? How does that fit in?
The loss function is telling us how wrong the model is.
Okay, so this false answer, it's the easy way out like the student memorizing answers?
Exactly. Our data's skewed, lots of false nodules. The model's basically taking the path of least resistance. It's easy for it to identify something that isn't a nodule when the overwhelming majority aren't.
Makes sense. So, what do we need to change?
We need a better way to reward the model for finding a true positive. Right now, it's getting a good score without truly understanding nodules. We need to design a better grading system, one that doesn't just reward false negatives.
So, a more nuanced grading scale? Like a more complex loss function?
Potentially. We need a grading scheme that punishes the model for ignoring important positives, the actual nodules, much more severely. We need to make finding the true positive much more valuable, so to speak.
So, we've got a model and a training loop. Big step.
Definitely. Crucial for any deep learning project.
But you say our metrics aren't usable yet? Why not?
Well, we're measuring something, but we haven't chosen the right metrics.
Like what? Accuracy? Precision?
Possibly, but maybe not. We need metrics that directly reflect the quality of our model's actions. Think about it like this. We're building an AI to play chess. Just because it makes a lot of moves, doesn't mean it's winning. We need a scoring system that rewards smart moves, not just any moves.
Right. So, we need better metrics in the next chapter.
Exactly. Chapter 12 will be about tuning and refining those measurements. We need metrics that align with the desired outcome.
We're logging to the console and graphing. Why aren't those metrics useful enough?
The console output, while useful, doesn't necessarily tell us if our model is working. Graphing might show us trends, but we can't look at a graph and instantly tell if the model is doing a good job. You need to tailor your metrics to the task. We need something more specific and more meaningful.
So, it's not about the tools, but the application of the tools.
Precisely. The metrics need to be relevant for the model's goal. We'll be talking about reward functions, specifically, in the next chapter. It's a crucial ingredient in reinforcement learning.
Interesting. Makes sense. So, we're laying the foundation now.
Exactly. This chapter gives us the basics. The next step refines our understanding and tools.